I love this old times table. In the last episode, I shared some rules and generalizations that fail at some point during your student's schooling. In this episode, I'm going to explore a common method for teaching a nines times table. Now, while this method doesn't fail as such, in my opinion, it is nothing more than a trick that should not be taught at all. So if you hang around to the end, I'm going to show you a much more appropriate strategy for teaching the nines facts or nine multiplications facts, and one that is consistent with contemporary approaches in mathematics today. And it goes like this. Place your hands in front of you. The finger or the thumb on the very left represents 1. Suppose you want to multiply 9 by 7. You fold down the 7th finger like this. 1, 2, 3, 4, 5, 6, 7. All the fingers to the left show that number of tens, and the fingers to the right show the number of ones. So with this example, 9 times 7 is 63. This will work for any of the basic facts. Watch this. 9 times 4. 1, 2, 3, 4. 9 fours is 30. They're the tens. 6. And 9 times 9. 1, 2, 3, 4. This is the ninth figure is 81. So that's the simple trick for the nines facts. But you can't really say it's a way of teaching the facts. It's really just a way of showing students how to use their fingers to show the products. So by doing that, they don't have to do any calculation, and they certainly don't have to remember the products. So in this way, you're really just teaching the trick itself. So why does it work? I don't know. When is it useful? It's only useful for teaching the basic facts, and I use that word teaching very lightly. So at best, it's only good for checking off 2 of the 3 criteria that are commonly used to assess the effectiveness of any strategy. So the first criteria is it efficient and accurate? Yes, there are 3 steps at most. 2, is it flexible? It does not allow me to see the turnaround fact. I can't show 9 sevens and then 7 nines. I can show the product, but not the complete fact. 3, is it generalizable to greater numbers? No, I can only use it for basic facts. Now let me show you a strategy that checks off all 3 criteria. But before I do that, I want to say that the prerequisite to learning this strategy is knowing your tens facts. For example, 2 tens are 20, 3 tens are 30, 4 tens are 40, and so on. Fortunately, children learn their facts involving tens first, as they are a natural part of counting. Now, using an array like this is really important, and I've shared this in previous episodes. But here I can see 10 threes, or if not 10 threes this way, maybe see 10 threes that way. One picture gives you the 2 facts and the commutative property. So if they already know 10 threes are 30 as shown by this array, then 9 threes must be 1 row of 3 less. So if the students need to learn or discover what 9 threes are, they can think, well, I know 10 threes are 30, 9 threes must be just 3 less. That's 27. Let's try another one. If the students already know 10 fours, they know 10 fours are 40, then 9 fours must be 1 row of 4 less, 36. Now we could also give the students a rule for calculating the nines facts, and symbolically it would look like this. Or you can simply tell them to calculate any nines fact, multiply your number by 10, and then subtract that same number from your product. But I don't know about you. I don't think too many 8 and 9-year-olds would be able to make sense of any of that. So I think it's best to give them an array, a visual picture, so they can conceptually understand how this strategy actually works. And once they understand that thinking, they can apply that strategy to greater numbers. Suppose you want to buy 9 apples at 25 cents each. I want your students to think, I don't know 9 by 25 cents, but I do know 10 by 25, which is $2.50. So 9 by 25 must be just 25 cents less, which is $2.25. And I can also generalize the strategy to problems involving 19. Suppose you want to buy 3 shirts and they cost $19 each. I want you to think, I don't know 3 19s or 19 threes, but I do know 20 threes are 60, so 19 threes must be just one lot of 3 less, which is 57 or $57. This thinking means the students understand the idea of building down from a known fact to figure out an unknown fact. And I hope you agree that here we can now check off all 3 criteria that we use to measure the effectiveness of any strategy. It is efficient and accurate, it is flexible, and is generalizable to greater numbers. Now, before I go, I'd like to take this opportunity to say I hope you're looking or exploring patterns involving the nines facts for multiplication. I hope you already know that a number is divisible by 9 if the sum of its digits is divisible by 9. So look here at the basic facts involving the nines multiplication facts. You will see that when you add the digits in the product, they all equal 9. Because 9 is divisible by 9, you know they are accurate. They are the correct products. But these can be applied to greater numbers. Take the example we looked at earlier. 9 by 25 is 225. Let's add the digits. 2 plus 2 is 4, plus 5 is 9, and we know 9 is divisible by 9. So that is an accurate product. You could also use a number line to complete equations like these. Then ask students to describe patterns they see in the products, in the equations, or on the number line itself. So this is what I want you to do. Number 1, forget about gimmicks or tricks. While they might be efficient, they are not flexible or generalizable, and they do nothing for learning or understanding. 2, focus instead on a strategy like this, which helps them build down from a tens fact they already know. And 3, use arrays like this to introduce a strategy and the activity that's in the link below to reinforce and practice the strategy itself. And finally, I would really appreciate if you give this episode a thumbs up and subscribe today so you never miss another learning episode with me. See you next time.